Consider module 5, question number 9a. Find the rank of the matrix by elementary row transformation. So how to find the rank of the matrix? Here you should know that. So when you consider the given matrix as A, consider the given matrix as A. So after considering the given matrix as A, the leading entry means this is called as a leading entry. Here this is what we call as leading entry. This one. First row, first element is called as leading entry. That element should be always non-zero. Keep in your mind that element should be non-zero. Make the below entries of that value as 0 by using that rule. By using R1, make R2 and R3 as 0. So I'm going to make that operation now. So non-zero, make those two elements as 0, and this is called as leading entry. Second row, second element called as leading entry, make that as non-zero, and below that value is 0. So the number of non-zero rows gives the rank of the matrix. The number of non-zero rows gives the rank of the matrix. That is what we should do now. So I will fix the row 1 and I will make an operation for R2 and R3. So that's why I am making that as R2 dash and R3 dash. So here R2 value is 2 and R1 value is 1. So R1 value should be multiplied by 2. So that's why I am multiplying by 2. So 2 minus 2 becomes 0. But in case of R1, R3, we have 1 here. 1 minus 1 will be 0. So I will just go by R3 minus R1. If we have opposite sign, go by R3 plus R1. That's all. So after applying that operation, R2 is disturbed. So similarly, next after making operation, the second row, second element will be called as leading entry. That should be a non-zero element. It is non-zero. Make the below element as 0. So now R1 and R2 is fixed. Making using R2. I am stressing R2. Using R2. Don't use R1 again. Using R2, make R3 value as 0. So if we have opposite sign, just add those two. R3 plus R1, R2. R3 plus R2 gives Z. Now we have a minus sign there, multiplied by minus. So therefore now the diagonal elements are non-zero. These two values are non-zero, and these two values are equal to 1. Always the leading entry should be 1 here. So therefore here non-zero rows are 2 rows. The non-zero rows means the whole row should be non-zero. The whole row should be non-zero. Means not equal to 0. All the values should have some values. All the entries should be having some values. So then such row is called non-zero. When you observe the third row, all the entries are 0. So that's why it is called a 0 row. So now I am counting the number of non-zero row. That is what I have ticked here. So these two rows are non-zero. Therefore the rank of that matrix is 2. This is the way of finding the rank of the matrix. Next we shall go for next problem. So apply Gauss-Jordan method for the given system of equation. So they are given the system of equation. Consider that system of equation. So here x1, x2, x3 are unknowns. This system of equation can be converted as in terms of matrix equation of the form Ax equal to B. So where A is a coefficient matrix, X is a column matrix, that is unknowns, B is a column matrix. So multiplying this matrix, you are going to get a system of equation. Now I am going to write an augmented matrix. What is an augmented matrix? A is to B. So what is Gauss-Jordan method? Reduce that augmented matrix to a diagonal matrix. Augmented matrix should be reduced to a diagonal matrix using only row elementary operation. Now consider the augmented matrix. A is to B. You know what is A, what is B. Note down that. Now apply an operation. As they have given Gauss-Jordan method, I should make the diagonal elements as non-zero. The non-diagonal element should be 0 there. So that is what called as a diagonal matrix. So here I am fixing R1. The value of your leading entry is non-zero. Make the below leading entry as 0 by using row operation. R2 and R3 is disturbed. R2 is nothing but R2. I am applying an operation R2 as R2 minus 2 times of R1. R3 as R3 minus R1. So I got. Next I am going to do, as I have a common term here, in R3, I am dividing that value by 2. So I am fixing R2. Fix R2. I am making these two values as 0 by using operation R2. Now we have a common element here, 2. Divide that by 2 and then fix that row. Fix the third row and make these two elements as equal to 0. By using R3. So now R1 and R2 dash are disturbed. I have fixed R3. So that is what I have done. So now the system of equation becomes 4 is multiplied by x, 4x equal to minus 2, 2y equal to minus 2, z equal to 1. Here x1, x2, x3 is unknowns. Therefore x1 equal to minus 1 by 2, x2 equal to minus 1, x3 equal to 1. Next, consider the problem. Find the largest eigenvalue and corresponding eigenvector by using Rayleigh's power method. For the given matrix A. And they have provided the initial eigenvector. Using that initial eigenvector, we are going to find the eigenvalue and eigenvector. So I am going to do an operation called Ax upon 0. X upon 0 means initial initial vector. So what is that? It is a column matrix. Just multiply that given matrix with column matrix. You are going to get an eigenvalue and eigenvector. One column matrix you are going to get. That is what 201. From that 201, when I multiply these two matrices, I got 201. Out of these entries, the value which is largest, divide that by largest value. So dividing by 2 here, we got 2 times of 1, 0.5. So therefore, the largest eigenvalue and eigenvector for the first iteration is 2 and 1, 0.5. Using this eigenvector 105, this vector is multiplied with again matrix A. So I am going to get Ax1 is equal to 2.502. So out of that 2.5 is the largest value. Take out that and get the eigenvalue and eigenvector. Again, simultaneously do the iteration unless you get the approximate values. The iterations should be the previous and the next iteration should be approximation should be lesser. Means the difference of those two values should be lesser. Just I am multiplying the matrix with the previous eigenvector. I am getting the largest eigenvalue out of that, and I am getting eigenvector. I have done 5 iterations or 6 iterations. I have done 6 iterations. I find out that here these two values are very much nearest values, approximations. See here 10.997, 10.999. So the difference is 0.002. Therefore, I can say that these two values are largest eigenvalue and largest eigenvector. So, largest approximate eigenvector and eigenvalue are eigenvalue is 3 and eigenvector is 1, 0, 1, as the value is nearest to 1. So I am rounding off that value to 1. I have written. This is the way of finding eigenvalue and eigenvector. We'll go for option. Solve by Gauss elimination method for the given system of equation. So they have given the system of equation. Consider the augmented matrix. So the Gauss elimination method says that you should reduce the augmented matrix to an upward triangular matrix by using row elementary operation. So here the leading entry is non-zero. Make these two elements as 0. So after making these two elements as 0, observe that this element is non-zero. If it is 0 and this is non-zero, interchange those two rows R2 and R3. Interchange those two rows and do the operation. So here I am applying operation for R2 and R3. So as the value R1 is 1, here multiply that one value by 3 and 2. So I got these two operations. So then I am going to fix R2 and make this value as 0. Just we have common term here. R3 minus R2 is enough to disturb R3 dash. So I got upper triangular matrix. Now I can rewrite this in system of equation form, and I can name that equations as 1, 2, 3. I got from the last value as z equal to minus 1. Substitute that value z in above equation, in equation 2. So I got y equal to minus 7 by 5. Substitute y value and z value in equation 1. In equation 1. This is in equation 1. Sorry, equation 1. I got 2.2. Therefore, x equal to 2.2 and y equal to minus 1.4, z equal to minus 1. And this is the upper triangular matrix. Next, solve the system of equation by Gauss elimination Seidel method. Gauss Seidel method. This is the system of equation they have provided you. So how to solve this problem is in the given system of equation, it should be said that we should set that diagonally dominant. What is diagonally dominant? The diagonal element should be more than the non-diagonal elements. The diagonal value should be more than the sum of the non-diagonal elements. 20 is greater than 1 plus 2. Yes, definitely. It is minus 2. Though it is minus 2, you should consider plus value. 20 is greater than 3. 20 is greater than 4 here. 20 is greater than 5. Therefore, I can say that the given system of equation is diagonally dominant, and we rewrite this equation in form of x, y, z. In form of x, y, z. So when I start with solution, the given system of equation is diagonally dominant. I came to know that. So therefore, we can rewrite that equation as x equal to 1 by 20 times of 17 minus y plus 2z, y equal to 1 by 20 times of minus 18 minus 3x plus z, z equal to 1 by 20 times of 25 minus 2x plus 3. So I am going with table construction. Here initially we should take the values of x, y, z as 0. If they provide you any other values other than nothing else, and they don't provide anything else, you should consider x, y, z as 0. If they provide you, you should consider those values as initial values. Initially, I am going to consider x equal to 0, y equal to 0, z equal to 0. Substituting that value, I got the first value of x as, and I substitute y value equal to 0, z value equal to 0. It is 17 by 20. If I calculate that one, I am going to get 0.85. Now the x value is 0.85. Substitute that x value as 0.85 in y and z value as 0. So I am going to get the y value as minus 1.0275. Then substitute x and y value in z. I am going to get that is what x, that is what z. I got the value of z. This is what first approximation. So now use these values to find second approximation. So x value takes 0.85, y value is this, z value is this. Substitute y and z value as here to get x2. I'm going to get the value of x2 as this, y2 as this, z2 as this. Substituting x1, x2, y2, z2. I'm going to get third approximation as the value is nearest to 1. So I'm rounding off to 1. So the values of x as 1, y as minus 1, z equal to 1 is the required solution using Gauss-Seidel method. Next, finally, we are going with the last problem of this module. The given matrix is a 2 cross 2 matrix. Reduce that matrix to a diagonal matrix. Reducing that matrix to a diagonal matrix. So the procedure of reducing to diagonal matrix is consider the given matrix. Solve this matrix by characteristic equation. Find the eigenvalue lambda 1, lambda 2. As it is 2 cross 2. If it is 3 cross 3, you are going to get 3 eigenvalues lambda 1, lambda 2, lambda 3. After finding eigenvalues, substitute those eigenvalues in a system of equation to get an corresponding eigenvector. After getting eigenvector, construct an model matrix. From that model matrix, find out P inverse. So after getting P inverse, diagonal matrix is defined as P inverse AP. So multiplying that P inverse AP, you are going to get diagonal matrix. Let us see how to solve. So the characteristic equation is given by determinant of A minus lambda I equal to 0. Just subtract the diagonal elements by minus lambda and expand that determinant and solve for lambda. I got the lambda values as 1 and 2 are the eigen values. Now I am going to construct an system of equation. Consider A minus lambda I, a matrix A minus lambda I, a matrix X is equal to 0 matrix. Expanding this, I am going to get an simultaneous equations. Minus 1 lambda x plus 3y equal to 0, minus 2x plus 4 minus lambda y equal to 0. Call that as equation star. When lambda equal to 1 in equation star, consider either one of the equation. You are going to get the same answer. So therefore, 2x equal to 3y, x equal to 2x equal to 3y I got. So when x equal to 3 and y equal to 2, the equation is balanced. That's why x by 3, y equal to y by 3. Therefore, the corresponding eigenvector for lambda equal to 1 is 3, 2. Is 3, 2. x1 equal to 3, 2 is the corresponding eigenvector for the lambda equal to 1. Now consider case 2. When lambda equal to 2 in star, I am going to get an equation of the form minus 3x plus 3y equal to 0. That is x equal to y. So we got x2 as 1 by 1, 1 is the eigenvector for lambda equal to 2. Therefore, the model matrix P is x1, x2. So write down x1, x2. Find det P. Find P inverse. P inverse is defined as 1 by det P into adjoint P. Now 1 by det P value is 1. Adjoint P is nothing but revert means alternate the values of diagonal elements. 3, 1 becomes 1, 3 and it means interchange the diagonal elements and the non-diagonal elements will be multiplied by negatives. So that is what P inverse I am going to get. So finally D is given by P inverse AP. Multiply all the 3 matrix. You are going to get diagonal matrix. That should be, the diagonal element should be lambda eigenvalues. Eigenvalues lambda 1 and lambda 2 is the diagonal matrix. So thank you one and all. I hope you all understood whatever I have said. So if you feel any doubts, please put a comment. And I feel that I went very fast. So I am putting the whatever the writing script I have done. I will put another video. So go through that thoroughly and solve all the problems. Thank you once again.